In 1960, I started working here.
Tell us a little bit about some of your early projects and what kind of work you were doing.
Well, I started working in what was then, I guess, the vision section.
Well, that's what I was going to ask. How did an experimental psychologist end up working in vision?
Well, psychology is a study of behavior, and one of the most important functions in guiding behavior is vision.
Oh, yeah.
So, and people who don't have vision have to learn how to function without that one sensory input, which is a very important sensory input, but people learn how to function without it. The important thing as far as the vision section, which eventually became the vision branch and then the vision laboratory after I became the head of it, the vision is extremely important for pilots of high-performance aircraft.
Sure.
And we were looking at issues that might threaten the lives of those pilots. As long as you're flying high and in no disturbance, they can function without vision for probably several minutes. But at a critical point in a high-performance maneuver, loss of vision can be fatal. And so we were looking at things which might produce loss of vision at a critical point in a mission. And that might be exposures to bright flashes of light. It might be exposures to accelerations which produce gray out and blackout, but not loss of consciousness, just loss of vision. And so those were the kinds of issues that we were looking at. And the question was how to provide protection against that type of vision loss. And of course, for the acceleration part of it, the pressure suits were the thing that provided protection against gray out and blackout, because it prevented or ameliorated the loss of pressure, blood pressure, which supplied pressure to the eyes. The pressure suit increases the blood flow to critical sensory areas, the brain, and lots of other parts of the body. But it also increases pressure in the eye, to the blood vessels in the eye, which ameliorates to a great extent the effects of acceleration on vision. The other thing, which is not quite as easy, not that that's easy to do, but not quite as easy to do, is to prevent changes in dark adaptation in the eye because of flashes of light. If you think about what happens when you walk into a movie theater, when you are light adapted, you walk into the movie theater and it takes a while before you can see anything but the screen if the movie is on. And that's because dark adaptation takes a much longer time than light adaptation. When you come out of that movie where you've been dark adapted for a couple of hours and walk out into bright sunlight, momentarily you can't see, but quickly you can see. So if you are dark adapted and your pupil is wide open and you're exposed to a flash of light, quickly you lose a good bit of dark adaptation and you can't see. And if you're a pilot, you need to see. You can't afford to lose vision for a second or two even. So we studied the effects of flashes of light. The problem is how to prevent too much light from getting into the eyes of a person who's at a critical point in anything. And so those were the kinds of issues that we were dealing with, and looking at the different sources of flashes of light, things like that. The other flashes that we were concerned about were flashes. At that time, people were very concerned about the possibility of nuclear war. And the flashes from a nuclear explosion reach very, very high points of intensity, so that was a concern. It needed to be protect it from actual damage, which you'd be concerned about with the infrared, as well as with the visual part of the spectrum.
But practically speaking, most acutely, it's just being able to see,
To
recovery of
be
that
able
vision.
to see, and the other thing, you'd be concerned a little bit about the ultraviolet part, because exposure to ultraviolet light can do very serious damage to the cornea and the anterior parts of the eye. And so that was a concern, but the major concern was the difficulty from the visual and infrared part of the spectrum, because those could destroy the vision immediately. Oh, and then later on, with the development of lasers, there again was a significant visual threat. And so we were looking not only at the causes of loss of adaptation, but what kinds of things might protect against the loss of adaptation. And as far as the infrared is concerned, you can put a filter on, because they don't need infrared light in order to see, but they need light in order to see, and that's the visual spectrum. And so we looked at things like rapidly changing filters, which would change to prevent a flash, a sudden appearance of light, and then clear up again very quickly, because you don't want the protection to blind you if it doesn't clear up quickly enough. So trying to define the parameters that are protective, some protective instrument should provide. We also looked at the use, and this was purely pilot driven, the use of night vision goggles for enhancing vision at night. And the night vision goggles had been developed for ground troops.
Okay.
They didn't have to worry about missing a mountain or something like that. So we set up some experiments, and one of the researchers in my lab went out to set up a night vision training facility for the Marines. The Marines were the main ones pushing for that at Yuma, Arizona. So he went out and established a training facility, and also we did some work to try to determine what kind of parameters they should be concerned about for pilots of high-performance aircraft using these things that were designed for ground troops, people walking around with them, not flying high-performance airplanes.